Today we are discussing about Unit 5. Today we are discussing about Unit 5. Operators on Hilbert spaces. Operators on Hilbert spaces. Operators on Hilbert spaces. Fourth unit. So we are discussing about today operators. Operators on adjoint operators, self-adjoint operators, normal operators, unitary operators. First, we will discuss about adjoint operator. Adjoint operators. Adjoint operators. Adjoint operators. Today we are discussing about Unit 5. Operators on Hilbert spaces. Operators on Hilbert spaces. Operators on Hilbert spaces. So 5.3. Adjoint operators. Adjoint operators. Adjoint operators. Adjoint operators. Let TB an operator on H. What is operator means what? So it is a tool. We have to change in the equations. It's called operators. So let T be an operator on H. T be an operator on H. Operator on H. H means what is H here? Hilbert space. So we have seen that T gives. We have seen that. We have seen that T gives rise to an operator T star. Seen that T gives rise to an operator. T star. Nothing but T star is a conjugate of T. T star is conjugate of T. T star is conjugate of 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 T on H star. On H star. Let T be an operator on H. T be an operator on H. T be an operator H. Star. Defined by T star F of X that equal to F of T of X, comma, X belongs to H, comma, F belongs to H star. It belongs to H star. H star. So since T star is also an operator on H. H star operator T star also gives rise to the operator T double star. Rise to the operator T double star. So means conjugate of T star. This means on H double star. H star. That means here properties. Here H double star equal to H. I think T double star equal to T. T double star equal to T. So let Y belongs to H. Here y tends to f of y. F of y. That tends to t star of f of y. That equal to f of z. That tends to z. But here y belongs to h. Y belongs to h. Where z equals to t star y. Another property, t star f of y. T star f of y into x. That equal to f of y t of x. That equal to t of x comma y. So t star f of y of x. That equal to f of z x. That equal to x comma z. That equal to x comma t star y. T star y. That means t of x. We are now clear the way. Means t of x. Here t of x t star f of y t of x. That equal to f of z of x. That equal to x comma z. That equal to x comma t star of y. 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 Then we are combining 1 and 2 property. We need to write third property t of x comma y. That equal to x comma t star of y. T star of for all x comma y belongs to Hilbert space. X comma y belongs to Hilbert space. So thus in a Hilbert space, the joint operator t is defined the equations. That means another property x comma t star of y plus z. T of x comma y plus z. T of x comma plus z. So that can be written as x comma t star of y plus t star of z for all x belongs to h. So similarly, t star of y plus z can be written as t star of y plus t star of z. T star of z. So similarly, x comma t star of alpha y can be written as x comma alpha t star of y for all x belongs to h. X belongs to h. Now clear the code. Next, we'll discuss a theorem. What is that? Five 4.3 theorem. 5.4.3. Next. So self-adjoint operators. One more definition. 5.4. Self-adjoint operators. Self-adjoint Before we discuss the adjoint operator, this is self-adjoint operator. Self-adjoint operators. So an operator T on Hilbert space, an operator T on Hilbert space, an operator T on Hilbert space H is said to be self-adjoint if T star equal to T star equal to T star equal to T. That means, so it is T is a self-adjoint. T is a self-adjoint. T is a self-adjoint. If and only if T of x comma y that equal to x comma T of y. For all x comma y belongs to Hilbert spaces. H means Hilbert spaces. Identity element, identity operator, identity operator I and zero operator is zero are self-adjoint operators. Self-adjoint operators. That means I star equal to I and 0 star equal to 0. Now discuss the theorem 5.4.3. 5.4.3. 5.4.3. Yeah, 5.4.3 theorem statement. The self-adjoint operator in BH, the self-adjoint operators in BH, from a closed real linear surface, closed real linear subspace, subspace of BH, and therefore a real Banach space. Therefore a real Banach space. Real Banach space. Which contains the identity transformation. Which contains the identity transformation. Now clear the board, clear the whiteboard, clear the canvas. Proof. This is the proof. Let X be a collection of self-adjoint operators. Let X be a collection of all self-adjoint operators. Self-adjoint operators on Hilbert space. On Hilbert space. H required to prove X is a closed linear subspaces. RTP means required to prove X is a closed real linear subspace. Real linear subspace. Real linear subspace of B of H by the above remark. That the operator O, O, I are self-adjoints. Here X is continuous zero operator identity, then thus X is non-empty. Thus capital X is non-empty. X is non-empty. Let A1 comma A2 belongs to capital X. Then A1 star equal to A1. A2 star equal to A2. So two real numbers alpha comma beta. Let alpha comma beta are scalars. Nothing but real numbers. Then we have alpha A1 plus beta A2, that equal to alpha whole star alpha A1 whole star plus beta A2 whole star that equal to alpha bar A1 star plus beta bar A2 star that equal to alpha A1 plus beta A2. Alpha A1, beta A2. A1, A2 are self-adjoints. So thus, alpha A1 plus beta A2 belongs to capital X. A1 comma A2 capital X real. This shows that capital X is real linear subspace of real linear subspace of B of H. Yes. Let us consider the sequence. Let us consider a sequence AN in X, in capital X, such that AN tends to A, that belongs to B of H. Then norm AN comma A tends to 0 as N tends to infinity. That means norm A star equal to norm A and A1 minus A2 whole star equal to A1 star minus A2 star. So now clear the canvas. Norm of here norm norm an star minus a star that equal to norm an minus a star plus norm an minus a tends to 0 as n tends to infinity. To claim a belongs to x, to claim a belongs to x, we show that a star equal to a star equal to a. That means norm a star minus a that equal to norm a star minus an star plus an star minus an plus an minus a. Here plus minus an star plus an star minus an plus an. Adjustment purpose we don't. That is less than or equal to norm a star minus an star plus norm an star minus an plus norm an minus a norm that equal to norm a minus an star plus norm an star minus an plus norm an minus a that equal to norm a minus an plus norm an star minus an tends to 0 as n tends to infinity. That means an star equal to an. Similarly, this thing. So thus an star equal to a star equal to a, which shows x is a closed linear subspace, which shows so capital X is a closed linear subspace of BH. Linear subspace of B of H. Closed subspace of complete space is complete. Closed subspace of complete space is complete. It follows that X is complete. X is complete. So follows X is complete. Hence capital X is real Banach space. Real Banach space, which contains identity element I. Which contains the identity element of I. The identity element of I, capital A. This completes the theorem. This completes the proof of the theorem. This completes the proof of this completes the proof. This completes the proof. Now clear the canvas. 5.4.6. 5.4.6. Theorem. 5.4.6. Theorem. Using operators. If T is an operator on Hilbert space, if T is an operator on Hilbert space H, Hilbert space H, then T of x comma x that equal to 0 for all x in capital X. If and only if T equal to 0. Proof. If T equal to 0, T equal to 0, we have T of inner product of T of x comma x equal to 0 for all x belongs to Hilbert space. Conversely, assume that T of x comma x equal to 0 for all x belongs to Hilbert space. Let alpha comma beta arbitrary scalars. We need two arbitrary scalars. Then we have T of alpha x beta y comma alpha x plus beta y alpha x beta y alpha x beta y alpha x beta y that equal to alpha of T of x plus beta of T of y comma alpha x plus beta y that equal to alpha into T of x comma alpha x plus beta y plus beta into T of y comma alpha x plus beta y that equal to norm alpha whole square T of x comma x plus alpha beta bar means conjugate nothing T of x comma y plus beta of alpha bar T of y comma x plus mod beta whole square T of y comma y T of y comma y that equal to 0 plus alpha into beta bar into T of x comma y T of x comma y plus beta into alpha bar T of y comma x plus 0 by hypothesis. So that equal to 0 equal to T of alpha x plus beta y comma alpha x plus beta y that equal to alpha into beta bar P of x comma y plus beta into alpha bar P of y comma x. That means alpha beta bar P of x comma y plus beta into alpha bar P of y comma x, that equal to 0. Here put alpha equal to beta equal to 1. We obtain T of x comma y plus T of y comma x, that equal to 0. Again put alpha equal to I, beta equal to 1. Then we obtain I into T of x comma y minus I into T of y comma x, that equal to 0. Now clear the canvas. Now clear the canvas. By adding 1 and 2 above equations, by combining the above equations, by combining the above equations, by combining the above equations, 2 T of x comma y, that equal to 0 for all x comma y belongs to Hilbert spaces. That means T of x comma y, that equal to 0 for all x comma y belongs to Hilbert space. It follows T equal to 0. Hence the theorem. So clear the whiteboard. Next. Normal operators. 5.5. 5.5 normal operators. Normal operators. Normal operators. 5.5 normal operators. Normal operators. An operator T on H. An operator T on H. Operator T on H. H means Hilbert space. Is said to be normal. Is said to be normal. Is said to be normal. T of T star equal to T star T. It is clear from the definition, every self-adjoint operator is very self-adjoint operator who is normal operator. Normal operator. Normal operator. Converse is not true in general, but the converse is not true in general. Not true in general. So next 5.5.2. 5.2, 0, 5.5. Statement: the set of all normal operators, the set of all normal operators on input space input space H is closed subset of BH. Subset of BH and is closed under multiplication and is closed under multiplication. Closed under multiplication. Proof. Let M be the set of all normal operators. Let capital M be the set of all normal operators on Hilbert space. Capital H. Hilbert space. So required to prove that RTP, what is here? RTP required to prove M is closed. M is closed. M is closed. M is closed. Subset of B of H. B of H. Let T be a limit point of M. T be a limit point M. Limit point M. Limit point M. Then there exists a sequence. T of M in M such that Tn tends to T. That means norm Tn minus T tends to 0 as n tends to infinity. Since norm Tn star minus T star that equal to norm Tn minus T whole star that equal to norm Tn minus T. It follows that Tn minus T, Tn tends to T. That implies Tn star minus T star to claim that T belongs to M. To claim that T belongs to M. Now clear the canvas. So we have to show that we have to show that T star equal to T star T star T. By hypothesis, we have by hypothesis we have Tn star equal to Tn star Tn for all n. Now T star minus T star T that equal to norm T star minus Tn star plus Tn star minus T star T numbers less than or equal to norm T star minus Tn T star plus norm Tn star minus Tn star Tn plus norm Tn star Tn minus T star T. Since Tn tends to T, Tn star tends to T star. That implies Tn, Tn star Tn star implies T star and Tn star Tn implies T star T and Tn star Tn that equal to Tn star Tn. We get that, we obtain that. Norm T of T star minus T star T that tends to 0 as n tends to infinity. Hence, T star equal to T star T. T star T. Thus T belongs to M. Thus T belongs to capital M. We now show that M is closed scalar multiplication. M is closed scalar multiplication. Scalar closed scalar multiplication That is for V belongs to capital M. And alpha scalar implies that alpha t belongs to capital M. Yeah. Since alpha t whole star equal to alpha bar t star, for any scalar we have, for any scalar we have, any scalar we have alpha t into alpha t whole star, that equal to alpha t into alpha bar t star, that equal to alpha into alpha bar t into t star. Now clear the canvas. Alpha t whole star alpha t so alpha t whole star here alpha t it means alpha t whole star alpha t whole star alpha t whole star alpha t, that equal to alpha bar alpha into alpha bar t star into t, that equal to alpha into alpha bar t into t star. T is normal here. T is normal. Hence alpha t into alpha t whole star, that equal to alpha t whole star into alpha t. Thus, alpha t belongs to M. For all scalars, alpha and t belongs to M. T belongs to M. Hence, 0. This completes the proof. This completes the proof. This completes the proof. Next, 5.4. 5.4. Here, an operator T on input space T on input space input space H is normal if and only 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 if norm T star of X, norm T star of X, T star of norm T star of X equal to norm of T of X, norm of T of for every X, for every X. So proof. What they given? An operator T on what? An operator T an operator T on Hilbert space H is normal if and only if norm T star X equal to norm of T of X for every X. For every X. So we have T is normal. T is normal. T is normal. T is normal. If and only if T star that equal to T star T star T. If and only if T of T star minus T star T that equal to 0. That means if and only if inner product of T star minus T star T X comma X that equal to 0 by theorem 4.6. That equal if and only if T star of X minus T star T of X comma X equal to inner product of T star minus T star T X equal to 0. If and only if T star X comma X minus inner product of T star T X comma x. That implies if and only if, that means t star x, comma t star x, that equal to t of x, comma t double star x. By definition of adjoint. By definition of adjoint. By definition of adjoint. Now clear the canvas. By definition of adjoint. That implies if and only if norm t star of x norm whole square that equal to norm t of x whole square, because since t double star equal to t double star equal to t double star equal to t. If and only if norm t star of x that equal to norm t of x, norm t of x. So 5.6.3. So unitary operator. So definition we'll discuss. 5.6 is unitary operator. 5.6 unitary operator. Unitary operator. An operator U on Hilbert space H. An operator U on a Hilbert space H. Hilbert space H is said to be unitary. Said to be unitary. Said to be unitary. If U star that equal to U star U that equal to I. I means identity. Clearly every unit operator is normal. Every unit operator is normal. Every unit operator is normal. Unitary operator is normal. But converse need not be true. But converse need not be true. Need not be true. 5.6.3 here we'll discuss. So one example also we'll discuss. 5.6.1 example. Let h equal to I power n be a real Hilbert space. Hilbert space with the inner product inner product, the inner product x comma y, inner product of x comma y equal to sigma I equal to 1 to n xi by I. Now let us define the mapping. Now let us define the mapping on H to itself follows itself follows P of x equal to y, where yi equal to sigma I equal to 1 to n aij into xj. xj. So, and aij is n cross n matrix such that aij ji coincide with the inverse matrix of aij. Then it follows that T star equal to T star T that equal to I, where T star represented by the inverse matrix of aij. 5.6.3. 5.6.3. Now we are discussing about 5.6.3. 5.6.3. 5.6.3. 0. If T is an operator, on inverse space H, Hilbert space H, then the following conditions are all equivalent to one another. All equivalent to one another. So first condition, T star T equal to I. Second condition is T of x, T of y that equal to inner product of x comma y for all x comma y belongs to input space. Third option, norm of T of x equal to norm of x for all x belongs to Hilbert space. Proof. 1 implies 2. 1 implies 2. Let T star T equal to I means identity. Now T of X comma T of Y that equal to X comma T star Ty that equal to X comma I of Y that equal to X comma Y for all X comma Y belongs to Hilbert space. 2 plus 3. 2 plus 3. Plus 3. Let T of X comma T of Y that equal to X comma Y for all X comma Y belongs to H. That means T of X comma T of Y that equal to X comma X by taking Y equal to X in the above equation. Above equation. That is norm T of X whole square equal to norm X whole square for X belongs to H. X belongs to H. Hence norm T of X equal to norm of X. Now here the canvas. Hence norm T of X equal to norm of X. 3 plus 1. 3 plus 1. Let norm of T of X equal to norm of X for all X belongs to H. Then norm of T of X whole square equal to norm of X whole square. X belongs to H. That is inner product of T of X comma T of X that equal to X comma X. That is X comma T star T of X equal to X comma I of X. X belongs to H. That is X comma T star Tx minus Ix that equal to 0 for all X belongs to Hilbert space. X belongs to Hilbert space. X belongs to Hilbert space. That is X comma T star T X comma T star T minus taking common minus I X inner product equal to 0. X belongs to H. This implies that T star T minus I equal to 0. Hence, T star T equal to I. This completes the proof of the theorem. This completes the proof of theorem. Proof of the theorem. Okay. So now clear the canvas. What we proved today. So what we proved today.